Okay, as we've discussed statistics thus far, we've gotten into some of the basics with mean, median, and mode. And then we spoke a little bit about standard deviation. And now we're going to turn our attention to normal distributions. So much of our data is normally distributed, and we'll define that in just a moment, that it's important to kind of recognize what that means and what that tells us. In particular, we're going to discuss normal distributions and what's called the empirical rule. So our objective, given a normal distribution, use the empirical rule to find a particular percent. Okay, so what do we know coming into this? We know what a standard deviation is, or what standard deviation is. Standard deviation is a typical distance between an individual data item and the mean. That's okay. We've also just defined it as a measure of how spread out the data are. Okay, as I just spoke to, many data sets are normal in that the numbers tend to cluster around a central value. They tend to cluster around the mean with no bias to the left or to the right. When graphed, these data sets resemble a bell shape. I'm sure you've probably seen this here and there in news items that have statistics involved, or various graphs that talk about the bell curve or a bell shape. Let's define normal distribution. A normal distribution is a graphical display of data in which the data tends to cluster symmetrically around a central value. It's also, it looks like a bell curve. Okay, that's where bell curve comes from. So now what is normal? What data sets are normal, and what data sets therefore have a graphical display that looks like a bell curve? Well, heights are normal. Weights are normal. Heart rates are normal. Test scores, battery lifetimes, intelligence scores, etc., etc. For example, let's take heights. Let's take female heights. Let's take the height of U.S. Female adults, and we'll find that there's an average height. I think it's around 5'4", maybe 5'5", and the vast majority of women tend to cluster around that average height. Okay, and then as you get taller and taller, you get fewer and fewer women. As you get shorter and shorter, you get fewer and fewer women. Okay, so here's the bell curve right here, and a normal distribution. Okay, the mean, median, and mode, one of the characteristics is the mean equals the median equals the mode, so it's right in the middle here. And we generally focus in a normal distribution on the mean. And you can see there's your bell curve shape, and it's symmetrical. Okay, you have 50% of data below the mean, 50% of data above the mean. And as you get further and further away from the mean, and either above or below, you have fewer and fewer data items that are represented. Characteristics, well, I mentioned the first one. The mean is equal to the median equals the mode, but we're going to focus on this line representing the mean. It is symmetrical about the center. Okay, the area under the curve is 1. Or we'll focus more on the fact that the area under this curve represents 100% of our data. As I said, 50% of the data values are less than the mean, and 50% are greater, and the area under the curve represents the likelihood as a percent of occurrence. Okay, because we're dealing with percents underneath this curve. Okay, so that's your normal distribution. Now, how does that come into play with Standard deviations, well, here's how that happens. The shape of the bell curve, taller and narrower, excuse me, excuse me, versus shorter and wider is defined by the data's standard deviation. So I found this online. We're not going to worry about it. It does say density over here. We're not going to worry about what it represents. What we want to see is that both of these curves, this one is a bell shape, again, and this one is a bell shape. This one here has a standard deviation of 15 in this case. The chart is right here. And this curve, the dashed line curve, has a standard deviation of 30. So the smaller standard deviation results in a narrower, taller bell curve or normal distribution. Because you go from 100 here, this is your mean, 100 in this example. You add 15, one standard deviation, you add 15 again. In this case, standard deviation of 30 represents it to be, means it's going to be shorter and wider as it, and so it's still a bell curve. Most things are still clustered in the middle, but they're not quite as clustered as they would be when a standard deviation is 15. Okay, no matter what shape, in other words, no matter if it's tall and narrow or short and wide or somewhere in between, no matter what shape, however, the percentages of the values that are within 1, 2, or 3 standard deviations of, above or below, the mean are always the same. And that's the beauty of the normal distribution. We can use it to give us information. My throat's not working very well today. Okay, so how is it, what have they found out about this? Well, they have discovered the empirical rule. In any normal distribution, the percentages of values that lie within 1, 2, or 3 standard deviations of the mean, and this is the wrong word here, are 68%, 95%, and 99% respectively. Okay, in other words, 68% of the data in a normal distribution lies within 1 standard deviation of the mean. That's a little over 2/3. So the vast majority, almost 2/3 of our data, or the majority of our data, lies within 1 standard deviation of the mean. Let's take a look at that with these 3 different charts that show this. Okay, there's the first 2 right there. So here is just a generic bell curve, a generic normal distribution, and again, this is the mean. Okay, you can see the bell shape. We know that 50% are above, 50% are below, and if we go out 1 standard deviation, we'll get to here. If we add 2 standard deviations, add 3 standard deviations, or subtract 1, subtract 2, subtract 3, etc. Well, between -1 and 1 standard deviation from the mean, okay, 68% of our values are there. Okay, between here and here, that's 2/3 of people will fall right in that region in a normal distribution. Okay, now let's recognize it's also symmetrical. So this is going to be 34% are within 1 standard deviation above the mean. And of course, 34% are within 1 standard deviation below the mean because of the symmetry. Now, if we go out to 2 standard deviations, as we've done down here, okay, we have now captured the vast majority, 95% of the data values, the data points, are within 2 standard deviations of the mean. Almost everybody is going to be clustered in this area of the curve. 95% under this curve has been shaded. You got a few people out here, and you got a few people out here, but 95% of us. So using my height example for women, for example, if the average woman is, 5 feet 4 inches is the number I used. That's going to be 5 feet is 64 inches. Okay, well, if the standard deviation is let's say 3 inches, so we go up 6 to 60 inches and down 6 to 48 inches, we're going to capture 95% of the heights of women, adult women in the United States, as an example. And we'll do a bit more with that with our example here. So 95%. Now, continuing to 3 standard deviations, and just give me a second here to get my notes together. Continuing to 3 standard deviations. Okay, we are now shading, I think I'm there, we're now shading almost everything under the normal distribution. 99.7% of people, of women in the case of my heights example, will fall within 3 standard deviations of the mean. Okay, that's how powerful the normal distribution is. It really tells us what's going on. Okay, well, if 99.7%, excuse me, are within 3 standard deviations, that means that this little piece and this little piece, those 2 pieces together represent 100 minus 99.7. Well, this represents 0.3% of the data points together. So this one is going to be 0.15%, and this one's going to be 0.15%. So in other words, for someone to be above 3 standard deviations from the mean or below 3 standard deviations from the mean means they're pretty darn rare. It's less than, it's less than 0.25% to be above 3 standard deviations from the mean, etc. Okay, and again, we'll label this the mean. Okay, so let's take a look at an example of this, and we'll see how this works. And I may have to come back and pull in my, if I can find my chart here. Yes, okay. So, okay, example 1. The scores on a certain achievement test are normally distributed with a mean of 500 and a standard deviation of 50. What percentage of the scores are A, between 400 and 600, and B, higher than 550? Okay, well, let's just quickly sketch a normal distribution. I like to start by drawing a line and then a mean, and then I just kind of, I don't get fancy. I just kind of try to make it look like, there you go. That's not, it's nothing great, but it gives me an idea of what's going on. Obviously, if you look at the 2 drawings here, mine's not great, but we're just trying to get a sense of what's happening here. So this is our mean. We've called it X bar, and we go 1 standard deviation up, 2 standard deviations up, and 3 standard deviations up, and we go 1 down, 2 down, and 3 down or below. Those are standard deviations above and below the mean. So there's our basic normal distribution, a basic bell curve. Now let's put in our values that we know. A mean of 500, so I'll put 500 here, and a standard deviation of 50. Okay, plus 1 means plus 50. That means this is at 550, this is at 600, and this is at 650. Add 1 standard deviation, add 2 standard deviations, add 3. Subtract 1 standard deviation to 450, subtract 2 to 400, subtract 3 to 350. So, let's remind ourselves. Okay, we have a mean score of 500. Well, we know that 68% of our scores are going to be between 450 and 550. Okay, they are within 1 standard deviation from the mean. If we go out a bit more, 95% of our scores are between 400 and 600. And finally, If we go even further to 3 standard deviations away, 99.7% of the scores on this achievement test are between 350 and 650. If you got above 650, you are a real rarity. If you got below 350, you're also a real rarity. Okay, so we're looking between 400 and 600. So we're looking what percent of the scores are in this area of the curve. Okay? Well, this is between -2 and 2 standard deviations. We go back to here and we see that between -2 and between 2 standard deviations is 95% of our values. Okay? So we notice that 400 is 2 standard deviations below the mean. 600 is 2 standard deviations above the mean. And since we are plus or minus 2 standard deviations, this tells us that 95% of the scores are between 400 and 600. It's a nice thing to know, trying to get a sense of what's really going on with this data. Okay, now that was letter A. Let me put an A here for you. Let's do letter B. I'm going to do a quick drawing again of the normal distribution. So again, I just kind of draw a straight line, then I draw a mean, and then I attempt to make a bell that is symmetrical. Perfection's not the goal. We know this is the mean. We know we go plus 1 standard deviation. We go standard deviations, adding them to the right, and we subtract them to the left. And we know our data, whoops, I need to get up here so you can see that. We know this is the generic standard deviation, normal distribution. We know we have a mean of 500, a standard deviation of 50. So add 50 again, add 50 again, subtract 50, and then subtract 50 for a third time. And so here's what we're going to work with. Now we want to know letter B higher than 550. Okay, well here's 550. 550 is 1 standard deviation above the mean. And we want to know what percentage of our data is in this range. And by the way, this goes on forever. But it obviously tapers off to smaller and smaller numbers. But what percentage is in here? Okay. Well, we want to use our symmetry and what we know. We know that half of the data, right? This represents 50%. Okay, so less than 500 is 50%. Okay, so now we've captured this part. What is this part in here? Okay, well, greater than 500 and less than 550, that's 1 standard deviation above. Okay, so we know that between -1 and +1 standard deviations, we know that this entire piece is 68%. And since it's symmetrical, although my drawing it's not quite symmetrical, we know that this piece is 34%, half of 68. So this is half of 68%, which equals 34%. So we know that from here to the mean is 34% of our data, and from the mean all the way down to the very end of the tail is 50%. So we want to know how much is above? Well, the whole thing is 100%. And then we're going to take off 50%, because that's not included. Then we're going to take off 34%, and we have a 16%. 16% of the scores are higher than 550 in this. Okay? So there you have it, a little work with the normal distribution as well as the empirical rule. Now, what's going to come up next? You might ask yourself, well, what happens if a number is like 510? How do you know what that represents? Or the number 430? I made use of the numbers that were exactly 1, 2, 3 standard deviations above or below, but there are a lot of numbers that are not exact. What about those numbers? Well, in the next video, we're going to talk about z-scores so that we can deal with those.